Okay, we're going to continue on here. We're in chapter 11, and we're talking really in this chapter really about electrons, and a lot of what we talked about sort of previously, uh, electrons as they transition from energy level to sort of energy level. It again does require your energy being absorbed, which is endothermic, for an electron to go up to a higher energy level. And eventually what will want to happen is those electrons again will want to relax back down to a lower state of energy, and that's going to require the atom to be exothermic and release that energy. And when it does so, that energy is going to come off as a wave. And as we talked about, the wave will have a specific wavelength, also a specific energy associated with it. And depending on where it comes out in that electromagnetic spectrum, as to what we may observe, again, if it comes out in the visible part of the spectrum, we will see a certain color. If it comes out as maybe some other parts of the spectrum, maybe you'll feel heat and that type of stuff. We talked about waves and ways to calculate some properties of waves. So c is equal to the wavelength times the frequency. C is the speed of light, 2.9979, I think. They want you to times 10 to the 8 meters per second. That is our wavelength, but it does need to be in meters in this formula. And that's our frequency, which does need to be in reciprocal seconds. Remember, you could use this to solve for either frequency or the wavelength if you have one or the other, just by dividing, basically. We can also calculate the energy associated with it. E is equal to h times the frequency. H is Planck's constant, so that is a constant value of 6.63 times 10 to the minus 34 joules seconds. Again, that is the frequency, also in reciprocal seconds. So the units that we do get for energy should be joules in this case, as the seconds will cancel each other when we multiply them and leave you with joules. We also could tie both of these sort of formulas together in case you don't know the frequency, but you do know the wavelength. E is equal to hc over the wavelength, and that comes from the frequency is equal to c over the wavelength here, and basically substituting that in will get you there. So you do have a couple of different ways you can get to the energy of a wave. You know the wavelength or the frequency. You can get to the energy, and obviously if you know the wavelength or the frequency, you can figure out one or the other there. We got into the last part here, I think last time, about Bohr's model of the atom, and it's sort of Bohr's model of the atom is sort of a planetary model of the atom, where we have our nucleus and we have these orbits where these electrons are moving around. And in this sort of model of the atom, again, we have some different energy levels. N equals 1 is the ground state, and that's the principal quantum number that's closest to the nucleus. You know, N equals 1, N equals 2, N equals 3. And this idea, as we talked about, of quantized energy, electrons, for example, will sort of gain and lose enough energy, as we talked about, to so fully make those transitions from one energy level to the next. So, for example, if we have an electron out here and it drops all the way down to, say, the first energy level, once again, that atom is going to give off that energy in the form of a photon of light. And that's a quantized sort of idea. The electrons are restricted, thank you, to either being in this orbit, this orbit, this orbit, or any of those orbits going around. They will not be in between. So remember, the sort of quantized idea of energy is like the staircase example. Again, you're either here, 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 or here, and you have enough energy to work your way up or down those stairs and not really end up anywhere in between. And the result of that for electrons, especially for atoms in the gas phase, what elements in the gas phase, they will give off a specific type of spectrum, and that's what's known as a line spectrum. And in a line spectrum, because we have these quantized changes in energy that correspond really to electrons transitioning from one energy level to the next. For example, this one would be an electron transitioning from one energy level to the next. This would represent another electron doing a different transition, and so forth as you go here. Clearly, I drew it all in red, but if it was in the visible part of the spectrum, they would have different colors at specific wavelengths. And that's what we see here. And a line spectrum is so unique that every element will have its own unique line spectrum. So depending on where you see the lines come out and depending on the wavelengths that you see, that will tell you what element that you're dealing with. And that's different. And this is what we sort of see in a quantized sort of version. In a continuous spectrum, we kind of see like everything coming out at once, and we don't see these distinct sort of lines. We see really all the colors coming out at once, and sort of the contrast to quantized energy would be something that gives off a continuous sort of spectrum, and that's more like a ramp type of situation rather than stairs. Again, if you're walking up a ramp, you pretty much could just stop anywhere you want, so you get everything coming off all at once, rather than in our quantized sort of version where, again, there's only restricted spots where you could kind of stop along the way. And that's sort of how electrons travel. There's only specific spots that they can stop along the way. They'll never find themselves sort of in between. Any questions on that stuff there? Okay. All right, so continuing on a little bit with our Bohr's model here, as I mentioned, sometimes referred to as a planetary model, is definitely not correct in all cases. It really does not hold up as you move away from hydrogen and more than one electron, but it does describe nicely sort of the lines that you do see in the hydrogen emission spectrum. And again, it's this orbital model where electrons move around these kind of pretty circles in these orbits. Does not really happen that way, as we'll soon talk about, but that is sort of his model of the atom. Again, possible places where you can find electrons are out in these orbits, and as they transition, again, they're going to transition fully from one to the next, wherever they may end up. And what we see in terms of, for example, those different lines is a result, again, of an electron dropping from a higher energy level to a lower energy level. So when we go from higher energy to lower energy, we get an emission spectrum because the atom's going to give off that energy in the form. And that's opposite of kind of what you get if the electrons go from a lower energy to a higher energy. That's sometimes an absorption spectrum, or just an absorption situation happening if your electron is starting lower and going higher. And again, the atom's basically absorbing that energy. It's endothermic, exothermic when it releases that energy as the electron comes down. Now, in terms of energy levels, whoops, come here. One of the things that we talk about is what's known as the principal quantum number. And there's actually 4 different quantum numbers. We will not talk about all 4 of them here in any great detail, but you will in the next class. But the one that we do deal with a lot here is the principal quantum number, and that's abbreviated with an N. And N stands for principal quantum number. It's a fancy way of basically saying energy level. And basically N could have values of 1 through 7. So there's basically 7 different energy levels within the atom where you could find electrons basically housed. As I mentioned before, N equals 1 is the ground state. That is close, lowest in energy, closest to the nucleus as you can get to. Anything above that, N equals 2, 3, 4, whatever it may be, those are referred to as higher energy levels. They are further away from the nucleus. So, we have N equals 1, and, N equals 2, N equals 3. Again, these are different energy levels within the atom of where we can find electrons. And again, as we kind of go this way, we are getting farther away from the nucleus and a little higher in energy. So as we talked about before, again, this transition in hydrogen, for example, of an electron from this energy level all the way down to this energy level gives off perhaps a blue color, while the transition here from this energy level to this energy level gives off only a red color. If you remember as well, when we looked at the electromagnetic spectrum and we had our Roy G. Biv in the visible part of the spectrum, red had a longer wavelength and it's lower in energy, as opposed to violet or purple, and obviously here's blue, has a shorter wavelength and it's higher in energy. So we see as well, sort of displayed here, difference in energy levels. So this electron obviously made a much larger transition in terms of energy. So the much greater amount of energy going from here to here results in more of a blue color coming off. Again, larger energy, probably shorter wavelength, going to give us that more blue color of the spectrum, as opposed to what we see over there in this transition on the left. Electron only had to go this far, so only this much energy was released, a little shorter, a lower amount of energy being given off in this case, lower energy, longer wavelength, more of a red color coming off. So depending on the colors that you see come off and those wavelengths that come off, again, you can make sort of a good estimate of how far that electron traveled. If you had an electron that had to travel many energy levels, that is going to result in the atom giving off that energy, a lot more energy, higher in energy, and probably a lower or smaller wavelength or shorter wavelength, as opposed to an electron just transition a shorter period of time. That's not as big of an energy difference that the atom's going to give off, and that's going to result in a longer wavelength, perhaps in terms of colors. We'll see that. For hydrogen, as we think we saw, there are 4 distinct lines that you see, each of them as a result of these transitions of electrons going from excited states or higher energy levels to lower energy levels. And again, our sort of idea of continuous energy versus quantized energy. Again, we get these distinct levels where electrons can be found. Once again, they will never be found kind of in between. They will always be either on this energy level, this one, or this one. Different here, and again, in a continuous, you can see it could pretty much be anywhere along the way. Thing from the sun, for example, gives off a continuous energy. You get everything coming out all at once. And again, our kind of ramp versus our staircase example that we've seen a number of times. Now, this Moore model, as I mentioned, does sort of work really well for hydrogen. But again, once you sort of move away from hydrogen, you get a lot more electrons involved. It really doesn't hold up. So we are going to kind of transition away from Bohr's idea of the atom. And there was a lot of sort of work done afterwards that did allow us to kind of move away from it. One of the important things that came along was done by a guy named de Broglie. And de Broglie basically just sort of theorized that he actually didn't do a lot of work, but his idea was this idea of light can behave like a stream of particles, and electrons can possess wave-like function. So sort of this dual nature of light that waves can have particle-like function, and electrons, which are particles, can have wave-like functions. And according to de Broglie, he thought of an electron bound to a nucleus as a standing wave. So if you think about it again, electrons are negatively charged and the nucleus is positively charged. So there definitely is going to be an attraction between them. And he sort of reasoned it kind of like a guitar string. So if you have a guitar string, obviously it is attached to the guitar, but you could pluck it and it will have both wave-like function, right? And your guitar string is not going to fly away, but it will have this sort of wave-like function. And that is sort of the idea that he had of how electrons in the atom are sort of tied to the nucleus like that. Also explains why maybe they just don't fly away, right? There's something holding them sort of within the atom and that attractive force. So because these particles could have wave-like functions, that makes a difference in terms of how they can move about the atom. And perhaps the way Bohr sort of described it in these orbits may not be so correct. And when we do look at a wave or any type of wave, there is a point where there is no amplitude in a wave, and that is what is known as a node. And in a lot of cases, what we'll see is when we think about sort of how electrons are in the atom and this wave-like sort of characteristics, the node is a lot of times where we see kind of like envision the nucleus is sort of at, is where that kind of wave has no amplitude. Now, the next big sort of step moving us away from sort of Bohr's model of the atom to this new wave mechanical model, which basically is this idea of kind of what Heisenberg said here, and this is the Heisenberg uncertainty principle. And the idea of the Heisenberg uncertainty principle is the more you know about how a particle is moving, a particle like an electron, the less you know about its actual location of where it's at. And vice versa, the more you know about kind of like where it's at, the less you know about like how it's moving and how it got to a particular location. And that's what's known as the Heisenberg uncertainty principle. And that is a major difference if you think about sort of the Bohr model of the atom, right? The Bohr model of the atom is like, hey, I got electrons in these orbits, right? They're circular, which means, hey, if the theory, if I put my finger there, eventually the electron will come back around the circle, right? Because it's just traveling these little pretty circles and stuff like that. So this idea of particles and wave-like function and this idea of, well, we don't really know at any given point in time how a particle is moving or where it's at is slowly moving us away from Bohr's model of, for certain, they're in these nice orbits, and I for sure know kind of how they're traveling and where they're traveling within the atom. Now, the last sort of major thing that moved us away from sort of Bohr's idea of the atom or model of the atom was done by Schrodinger, and he did a bunch of what are referred to as Schrodinger equations. These are what are sometimes referred to as wave functions. A bunch of calculus that if you ever take physical, you'll do a bunch of them. Idea of a all right, we went from kind of Bohr's idea of they're in these orbits, they're moving around pretty circles, and I for sure know kind of how they're moving. This idea of de Broglie, Heisenberg, and now Schrodinger of we're not really sure how it's moving an electron. We're not sure exactly where it's located. The best we could do is come up with the idea of there's a high probability of finding an electron in a particular location in an atom. And we're not really sure how it got there. We're not really sure how it's moving, but there should be a pretty good chance of finding an electron in a particular location within the atom. And again, if you just think about the nucleus is positively charged overall, so there should be a pretty high probability somewhere near the nucleus of finding an electron. Again, it doesn't mean you know how it got there, you don't know how it's moving, but you know, if you had to take a bet, there should be a pretty good chance of it. As you sort of move away from the nucleus at some distances, the probability of finding an electron is a lot lower than, say, near the nucleus. Doesn't mean you cannot find an electron out away from the nucleus. It just means perhaps you have a much better opportunity of running into an electron if you're closer to the nucleus. So the idea of what happens sort of with these sort of equations is they come up with sort of what are known as electron density maps or probability maps. And we move away from Bohr's idea of these nice, pretty orbits to this idea of we think electrons are housed in the atom in what is known as an atomic orbital. And an atomic orbital is really a probability map of, you know, you have a pretty good chance of finding an electron in this area of it versus some other area. There are several different types of atomic orbitals we'll talk about. There are s orbitals, there are p orbitals, there are d orbitals, and there are f orbitals. And again, these are theoretical sort of places within the atom that technically have shapes based on these sort of calculations and where you can find the electron in. In any situation, though, one thing that you should keep in mind is any type of orbital, if I represent an atomic orbital here by a line, any individual orbital could hold a maximum of 2 electrons maximum. If each of these arrows represent an electron, it could only hold a maximum of 2 electrons. So any individual s orbital, p orbital, d orbital, or f orbital could hold a maximum of 2 electrons. Doesn't mean they have to be filled with electrons, but if you were going to max them out, then that's how many that you could put in there. And this is an idea of a probability map. And again, I think you can see it actually on the screen, not too bad in this room. That kind of darker area, again, is a higher probability of finding electrons, as denoted by the darker red color here, or pink color. And obviously, as you sort of fan out from the nucleus's region, which is probably in this area, you can see it's getting lighter, but there's still a probability of finding an electron in there. Again, that doesn't mean the electrons are moving in pretty circles. It means the electrons are in this space and they're, just kind of moving around in random sort of places and directions. We're not really sure exactly how they are or where they're located based on Heisenberg's uncertainty principle. So let's talk about each of these orbitals. The first type of orbitals that can hold an electron are s orbitals. And s orbitals actually start on the n equals 1 level. So the ground state, the very first energy level, you will find an s orbital. And that's referred to, by the way, as a 1s orbital. The 1 means it's on the first energy level, and you will find an s orbital on every energy level. But when you go to the second energy level, it is no longer an s orbital. It's now known as a 2s orbital. The 2 meaning it's on the second energy level, basically, and it's a s orbital. 3s, 4s, 5s, and so forth. So on every energy level, starting with the first one, you will find s orbitals. S orbitals are basically spherical in shape, with sort of the nucleus in the middle and high probability. As we just saw on that previous map there, where you have a high probability of finding it. The size of them does get larger as you go up the energy levels, and that's just to accommodate all the extra electrons that are there. So they have the same shape, but they do get larger as you go up energy levels to accommodate. Here's what an s orbital looks like.
An s orbital has a spherical shape with the nucleus at the center.
And again, you can sort of see the electron density map on the left and sort of the shape there of our s orbital. Again, these are probability maps that came out of the Schrodinger sort of equations, where you could find sort of electrons. And as you can see, it just sort of increases in size as you go from one energy level to the next. Again, the 1 here means it's on the first energy level, 2 means it's on the second, 3 means it's on the third energy level. So again, those numbers in front of the little letter will tell you basically what energy level you're on. Now, p orbitals actually start on the second energy level. There are no p orbitals on the first energy level. You don't start to see p orbitals until you hit the second energy level. So on the first energy level, all we have is an s orbital. When we get to the second energy level, we still have an s orbital. And here we actually have p orbitals occur. And there's actually 3 different types of p orbitals. There's a px orbital, a py orbital, and a pz orbital. That is their location in 3-dimensional space. One's on like the x-axis, the y-axis, and the z-axis, kind of like a math little Cartesian plane there. And in this case, the maximum number of electrons that you could do is actually 6 electrons. And that is because a couple of different things. When we look at an s orbital, there's only one type of s orbital. No matter what energy level you go to, there's basically only one type. And that means you can max out with 2 electrons max. When we go to the p orbitals on any energy level where there are p orbitals, there's not just one p orbital. That's the px, that's the py, and that's the pz orbital. So there are 3 different individual p orbitals. Each one could actually hold 2 electrons, which means if you filled all of those p orbitals up on any energy level, it could max out with 6 electrons, 2 in each of the individual orbitals, 2 in this orbital, 2 in this orbital, and 2 in this orbital. When you are on a energy level and you have more than one of the same type of orbitals present, a grouping of individual p orbitals on the same energy level, like here, this is sometimes referred to as a sublevel or subshell, depending on your book. Most of the time, people go with the shell these days. That is known as the 2p subshell. And the 2p subshell represents all 3 of those p orbitals. They're on the second energy level together. We don't use the word subshell or sublevel with s orbitals because there's only one type of s orbital. There's not multiples, so we just call it an s orbital no matter what energy level it's on. But when you have multiples of the same orbitals on the same energy level, it's referred to as a subshell. Any questions on that there? And here's what the p orbitals look like. They kind of look like a figure 8 or teardrop sort of shape.
The 2px orbital is in the shape of a figure 8 along the x-axis.
Here's the y.
The 2py orbital is in the shape of a figure 8 along the y-axis.
And then obviously we have one on the z as well.
The 2pz orbital is in the shape of a figure 8 along the z-axis.
So I don't think it'll let me write on that. Well, no. So if you kind of look at the shape, this idea, this is what is referred to as where the node would be, no amplitude, kind of like where the nucleus would be. And again, in terms of probability of finding an electron, you probably have the highest probability near that point. On either side of those lobes is where you would find the electron. And as you can see here, again, nucleus sort of assumed here, and you can see the highest probability is, near that spot there in each of those spots along the way. So again, all three of these together on any energy level are known as a subshell, and you can put 2 in there, 2 in there, 2 in there for a grand total of 6 electrons if you fill up the p subshell. So first energy levels is where we first start to see the S's. We have to wait to the second energy level to kind of see p orbitals appear. So that brings us to the next type of orbitals, which appear on the third energy level. And these are the d orbitals. And the d orbitals, again, start at n equals 3. So again, on the first energy level, we have our 1s orbital. On the second, we have a 2s orbital. That's where we first saw our 2p subshell occur. On the third energy level, we have a 3s. We also still have a 3p. Again, you'll see kind of p's on every energy level after that. And this is where we first start to see our 5 different d orbitals. So our 3d orbitals over here. And since there are 5 different d orbitals, once again, all 5 of these individual orbitals here make up the 3D subshell in this case. And because there are 5 of them, each one could hold 2, which means I can put 2 into this guy, 2 into this guy, 2 into this guy, 2 into that guy, 2 into that guy. Which means if you filled up the D subshell on any level it is present, it could max out at 10 total electrons. So you could put 10 total electrons in there. As you can kind of see here, based on the picture, d orbitals are kind of like 2 p orbitals put together. The last one's sort of like a donut with a p orbital going through the middle of it as well. Again, this is where we have most of our electron density happening, nucleus sort of in the middle, and most of our electron density happening. In this case, we have a lot of it kind of coming around the ring there in the middle as well. And here's what they sort of look like.
Y squared orbital has a cloverleaf shape that lies in the xy plane and is aligned along the x and y axes. The
3dxy orbital has a cloverleaf shape that lies in the xy plane and bisects the x and y axes. The
3dyz orbital has a cloverleaf shape that lies in the yz plane and bisects the y and z.
The 3dz squared orbital is shaped like a pz orbital with a donut of electron density around the center. It is aligned with the z-axis.
So again, everywhere there's sort of those greenish areas and those orbitals, a probability of where you could find an electron in an atom. Do these shapes really exist? No, you probably won't see those shapes. Again, they're just theoretical sort of maps of where you could find these electrons in an atom. Lastly, the last type of orbital that you would come across happens on the 4th energy level. When you get to the 4th energy level, that's where we start our f orbitals. And once again, there are 7 different f orbitals. So again, our n equals 1, our 1s, our n equals 2, 2s, and our 2p, our n equals 3, 3s, 3p, 3D. I'll start up here. N equals 4. 4s, 4p's available. 4D, and again, maybe I can squeeze it in there. I'll try 1, 2, 3, 4, 5, 6, 7. And that is where we first start to see our 4f orbitals appear. Again, this would be referred to as the 4s subshell. Once again, as you can see, they kind of look like two d orbitals put together here. And again, each of these could hold 2 electrons. So 2 electrons, 2 electrons, 2, 2, 2, 2, and 2. And again, if you add all that up, 2, 4, 6, 8, 10, 12, 14 maximum electrons if you filled up a F subshell. So those are really important things to know, obviously. The S, the P, the D, and the F. How many electrons total if you fill up the orbital or the subshell. And if you know that, you'll be able to write sort of what's referred to as electron configuration for pretty much everything you need. Also, if you know, and you should know when each of those starts. So on the first energy level, that's where S's start. Second energy level, that's where P's start. Third energy level, that is where D's start. And fourth energy level, that is where F starts. That will also help you make something that will help you get the electron configuration pretty easily. So let's continue on and talk about that. So the energy of these orbitals as we go from lowest energy to highest, that, by the way, is how electrons will go into the atom and are filled into the atom. They fill the lowest energy electrons orbitals first, and then they continue on their way and kind of fill the next lowest, the next lowest. So electrons always go into the atom, lowest energy first to highest, and they go until basically all the atoms are basically all the electrons are distributed within the atom. This again would be our n equals 1. This would be our n equals 2, our n equals 3, and our n equals 4. By the way, there's an n equals 5, n equals 6, n equals 7, n equals 6 and 7 all the way up there. Now, we talked about these guys being subshells. There's also a terminology known as, if you took all the orbitals, for example, on a particular energy level, that is what is known as a level or a shell. So for example, if I wanted to know the maximum number of electrons in the n equals 2 shell, the answer would be, I could put 2 here, 4, 6, and 8. 8 maximum electrons. So that again is different than some other questions. So for example, if we want to know the maximum number of electrons in a 3D subshell, the maximum number of electrons in the n equals 4 shell, and the maximum number of electrons in a 3p orbital. Why don't you take a moment and think about how many electrons in each of those cases. All right, let's take a look. First one is the maximum number of electrons in a 3D subshell. That should be how many? Should be 10, yeah. And that would be all these guys right here. That whole thing is the 3D subshell made up of 5 different orbitals. You could put 2, 4, 6, 8, and 10 electrons in there to fill it up. Question on that one there. Now, the maximum number of electrons in the n equals 4 shell, that is, technically speaking, everything on this energy level here. And again, you could go 2, 4, 6, 8, 10, 12, 14, 16, 18. And I kind of didn't have my 7 here. 3, 4. It's because I ran out of room, I think. But we could put another 14 there, right? So was that 32, I think, if I am not mistaken there. Lastly here, how many electrons in a 3p orbital? The answer is 2. And that's because could be that orbital, could be that orbital, or could be that orbital. Not sure which one we're talking about, but each individual orbital could only hold 2. Now, if the question was different and want to know how many electrons in a 3p subshell, then the answer would be 6, because it would be all of them together. But in this case, it just want to know in the orbital, and any orbital can only hold 2 electrons. Any questions on that there? Now, you may not want to draw this to figure out, for example, how many electrons there are you could fill up on a particular energy level. So if you want to know the maximum number of electrons on an energy level, you basically just take 2 times n squared, n being the principal quantum number. So for example, here, that is the second energy level. So you square it first, gives you 4 times 2, which is 8 electrons, which is what we counted up there. If you do the one we did up here, n is equal to 4. 4 squared times 2, that gives you 16 times 2, gives you 32 electrons. So again, that's sort of a quick way that you could calculate how many electrons to max out a particular energy level without maybe wanting to draw it, especially if you got like, the 6th energy level or 7th. By the way, there are orbitals that go beyond F, but you'll never come across it based on anybody on the periodic table. F is where you max out. After F, they just kind of go alphabetical at that point, so like G and so forth. But you'll never get there with anything on the periodic table. It maxes out really in the F orbitals. This is kind of as far as we go in terms of orbitals. Any questions on that there? Now, what we see here before I, scribble all over the board here. Let me erase that real quick. Now, what we see here on this energy map here is when we look at like the n equals 1, n equals 2, n equals 3, and so forth, everybody on the third energy level is perfectly equal with each other. Everybody on the second is perfectly equal with each other in terms of the orbitals. And once we get more than one electron involved in an atom, because electrons are ultimately negatively charged, they really don't want to be near each other. So when you get a lot of electrons kind of near each other, what ends up happening is the orbitals kind of move a little bit in terms of their energy. So instead of everybody being perfectly nice and lined up like we see with hydrogen, if you take a look here, you can see there's a big old shift in the energy level of the orbitals. And that affects how electrons go in, because they will fill up the lowest energy first, then go to the next, then go to the next, then go to the next, and they'll continue this pattern. And where it messes most people up is it goes from 3s to 3p. The next lowest in energy is actually the 4s, and then we come back to the 3d. So, and that pattern follows. 5s gets filled before you go to the 4d. So there's this shift in energy that affects how the electrons go in there. So you do want to make sure you know the proper order of how electrons go in. And let's take a look at that. This is the proper order of how electrons go in. And if you know this, and you know what we talked about, that you can max out an s orbital with 2 electrons, a p subshell with 6 electrons, a d subshell with 10 electrons, and an f subshell with 14 electrons. You should be able to write any electron configuration that you'll need to do. How does this work? You always start up here, and basically what you do is you just follow the arrows. So you put your electrons in there first, and once you're done, you zigzag back and just keep going. And you keep going until you have basically put in there as many electrons as you need. And you can see if you follow this, you go from your 3p to your 4s, and then back to your 3d and so forth. So you just keep zigzagging through it. Now, obviously, you need to know the proper order. So a second ago, I said what's really important for you to remember as well is on what energy level does each of these orbitals begin. So if you remember, I mentioned on the first energy level, that is where we see our s orbitals begin. And if you want to recreate this chart here on your paper, you can do this very, very simply by going 1s. On the second energy level, that's where we see p start. So you just go down to the right a little bit and go 2p. On the third energy level, that's where d start, go down to the right a little bit, go 3d. On the fourth energy level, that's where f start, go down a little bit to the right, go 4f. if you could remember 1, 2, 3, 4 and the letters that go with it, you could pretty much recreate this thing on the left pretty simply, because now all you have to do is just fill in the numbers underneath each of those. So just go like 2s, 3s, 4s, 5s, 6s, 7s, 2p, 3p, 4p, 5p, 6p, 7p, 3D, 4D, 5D, 6D, 4F, and 5F. Now look, even if you go too far, you put them all sevens, it doesn't matter, you'll never get there anyway. So even if you go too far with the numbering, it won't make that big a difference. Once again, you start up here and then you just draw your arrows. And again, you have basically just recreated that thing pretty simply by remember 1, 2, 3, 4. And again, you'll get the right sort of order as you go through there. And you know, you could come through here and continue on your way there. So that's a really easy way to just recreate this order on the paper. If you're not sure, kind of go diagonal to the right there, go 1, 2, 3, 4, fill in the numbers and the letters and just draw some arrows in there, and you'll have the order that you need pretty simply on your paper. Any questions on kind of how to do that there? Okay, so this again is from your book, the order, and again you can see we go from kind of the 4s into the Ds, and then the 5s into the 4Ds along the way. So let's talk a little about writing electron configuration. Electron configuration tells us how the electrons are distributed within the atom. If we have a neutral atom, what we know is the number of protons should equal the number of electrons. So if something is neutral and you want to write an electron configuration for it, if you know the atomic number, which you should from the periodic table, you could write the electron configuration because it should have the same number of electrons as its atomic number. All right, so let's take a look at one. We're going to start with hydrogen. And again, we would start here at the very top. And hydrogen, which is atomic number 1, has 1 electron. That will take us right here to our 1s orbital. And that's where we would put our electrons in. Our electron configuration here would be 1s1. And that is how you say it, and that is how you word it there. 1s1. Not 2, but 1, if I write it right there. There we go, 1. So what does each of these sort of things mean? This is the energy level. That is the N number, the principal quantum number. The S here tells us we're in the S orbital, or sometimes it could be a subshell, but in this case it's just an orbital. And the number up on top is the number of electrons in the orbital, or again, if we're talking about a subshell. And that is how it should be written, and that's how you say it, 1s1. Again, the first number is a regular size number, the letter is a lowercase letter, and it's a superscript up on top is the guy, how you should write it. Now, we could also represent electron configuration through what is known as orbital diagram. An orbital diagram is either using a box to represent an orbital or a line to represent an orbital, and these guys could represent orbitals. And we use arrows here to represent electrons. So arrows for electrons, boxes or lines for orbitals. So in this case, if we were to draw our orbital diagram, we basically need 1 box or 1 line to represent the 1s orbital, and we would need 1 electron that would go in there. The first electron will always go in the upwards position, and facing upwards is always the first electron in the box. So 1s1 is the electron configuration. The line or the box with the arrows is what's known as orbital diagram that represents the electron configuration. We could also see from that box that we could put a total of only 1 more electron in it before it is full, right? Because we could only put 2 electrons in. So let's continue on to the next element, which is helium. And before we do, it brings up an important thing, which is Pauli's exclusion rule. And Pauli's exclusion rule says that no 2 electrons that are in the same orbital can have the same 4 quantum numbers. Now, as I mentioned before, we really don't talk a lot about quantum numbers in here. When you take 1A, you'll talk about all these things. But just to tell you, there are 4 quantum numbers. There is the N, there is the L, which is the angular quantum number. There's a magnetic quantum number, which is M sub L, and there's a spin quantum number, which is M sub S. So these are the 4 quantum numbers here. We only kind of deal with N. N is the energy level, basically, as we talked about. For the most part, L will basically tell you the type of orbital you're dealing with. M sub L will tell you how many there are. And really, it is the orientation in 3-dimensional space. Like, for example, Px, Py, and Pz is basically what that tells you. And the S is actually the spin on the electrons within those orbitals. So these are the 4 quantum numbers. And again, you don't really have to worry about that other than N, which is what we talk about here in this class. But the idea of Pauli's exclusion rule tells us that when we put, for example, our second electron into our orbital in any type of orbital, 1s, 2s, it doesn't really matter, 2p, it has to obey that rule. So I'm going to just tell you kind of what the values are for the 4 quantum numbers so you can see why it has to go in a certain way. If we were going to do, for example, for this first electron we just did, and we wanted the 4 quantum numbers, N would equal 1 in this case because, frankly, it's on the first energy level. L in this case would equal 0. And what does an L equals 0 mean? It means you're talking about an s orbital, which is where this electron's in. So it would have a value of 0. M sub L, because there's only one type of s orbital, it would also have a value of 0. And in this case, the spin is what is referred to as plus 1/2. And that's because the electron here is facing upwards. So when an electron faces upwards, plus 1/2 is the spin. When it goes downwards, it is minus 1/2. And that is what is known as a spin because electrons do have a spin, is affected by electrical fields and so forth. So what that means is if I decided to put this electron, the next electron, into this orbital, I have basically 2 options. I could either put the electron in going in the same direction, or I could put the electron in going in the opposite direction. So if I took this first electron and did the 4 quantum numbers, I would get this. If I put it in the exact same way, I would actually end up with the same 4 quantum numbers. And that is a violation. You can't do that of Pauli's exclusion rule. So we don't do that. We never put electrons in going in the same direction. How we get around it is when the second electron goes in, it actually has to go in the opposite direction. Now, just to show you how we get around it, the 4 quantum numbers for this, which you would not be asked to ever do in this class, is N is equal to 1. L is still equal to 0 because it's still an s orbital and it's still on the first energy level. The M sub L is 0. Now the difference and where it does not violate Pauli's exclusion rule is the second electron is pointing downward, which means instead of plus 1/2 for the spin, it has minus 1/2 versus plus 1/2. That gives them different 4 quantum numbers, even though 3 of the 4 are the same, but overall they don't have the exact same 4 quantum numbers. And that does not violate Pauli's exclusion rule. And that is the way that the electron will go in there the second way. This, by the way, is what is referred to as having paired spin. When you have 2 electrons in the same orbital heading in opposite directions, their spins basically cancel each other out. Plus 1/2 minus 1/2 equals 0, basically, when you add them together, and they cancel out their effects on each other. So the take-home message on this one is if you put the second electron into the orbital, it does need to go in the opposite direction, which is down. The first one should always go up when you're doing orbital diagram. Second one goes down. Any questions on that there? All right, so let's see, that does happen with helium. So once again, we would start with helium that has 2. We're going to always start back up here. We could definitely put it in there. So that's going to take us to there. And that's going to get us here a 1s2 for the electron configuration for helium. We can now do our orbital diagram where our first electron again will go up. And again, not to violate Pauli's exclusion rule, our second electron will have to go in the down position. And again, that is what is referred to as having paired spin. Can I put any more electrons in this 1s orbital at this point? It is filled, right? Which means if I have more electrons, I need to continue on my path. And now I will have to go from here and zigzag back and now head up here. And that happens at the next element, which is lithium, which has 3 electrons. So we have lithium here with 3 electrons. Again, it would be 1s2, 2s1 in this case. Again, there is no dashes, there's no commas between these things. It just is written straight across. Now, this means that on the first energy level, I have 2 electrons. On the second energy level, I have 1 electron. Yeah. And again, that's n equals 2 level. This is n equals 1 level. So I have 1 electron on a higher energy level in this case and 2 electrons on a lower energy level. If we were to draw our orbital diagrams, we would need a box for each of them. Now, if you really want to draw orbital diagrams correctly based on energy, you would actually be drawing your diagram like this, 1s, and we know 2s comes above it in terms of energy. I am not going to draw it based on energy because I'm going to run out of room, so I'm just going to go sideways here with it. But truly, to kind of do it correctly in terms of energy, you would have to obviously separate them out by energy, kind of go upwards. But I will eventually run out of paper if I kind of go that way, I think. So I'm just going to go sideways. We're going to go first electron in, second electron in the opposite way. And now our first electron will go again in the upwards position. And you can see that we now have basically room for 1 more electron in that s orbital, that 2s orbital before it is filled. So let's put it in there. That happens with beryllium. Beryllium has 4 electrons. So again, starting here, we can put 2 in there. We could zigzag back around and put 2 into there. So let us do that for beryllium, which has 4. And its electron configuration would be 1s2, 2s2. I now have 2 electrons on the second energy level, and I have 2 electrons on the first energy level in this case. And our orbital diagram would look like so. Again, we would go up on the first one, down on the second one, up on the first one, and down on the second one in this case. And again, at this point, we're now full in terms of our second energy level there, our not second energy level, but our 2s orbital there. We would have to continue on and put them into the next available lowest energy orbital. And that happens obviously with number 5 there, which is boron. So let's take a look at boron and see what happens with it. And boron, which is 5, once again, always going to start up here. So we could put 2 into there, zigzag, we could put 2 into there. And now we're going to come to the 2p subshell, which actually could hold a total of 6. Not that we have to fill them all up, but it could hold 6. So we definitely are going to be into that subshell. So let's take a look at the electron configuration. Should be 1s2, 2s2, 2p1 in this case. How many electrons do I have on the second energy level? How many? Anyone? How many do I have on the second energy level? I have a total of 2, and 1 more makes 3. Yeah. So both of these are on the second energy level. On the first energy level, I have 2 electrons still present. That means when we do our orbital diagram, again, we would actually need not 1, not 2, but we would need 3 boxes to represent the 2p subshell, as there's a px orbital, right? A py orbital and a pz orbital, right? That makes up that 2p subshell. Putting in our electrons here, right, put them in. We go up 1, down 1, up 1, down 1. And now when we get to the subshell, we do work left to right here, and we would put our 1 electron into there. You can see that hopefully we have 5 more electrons that we could put into the 2p subshell before it is filled up, and we would have to move on. So we still have plenty of room to sort of fill up this 2p subshell. So let's fill it up there. So we'll go to carbon number 6, and carbon number 6 there would again start up here. That would put 2, 4, and obviously we have room in there to put our 6 in, and we would zigzag around like so. Now, there is a rule as to how an electron will go in. We're talking about is like the 2p subshell, and on the 2p subshell we have our px, our py, and our pz orbital. We've already put our 1 electron in here. Now our other options in terms of where we could put electrons are, we could pair it up, or we could instead move to the next one. And there is actually a rule that tells us which way we want to do it, and that is what is known as Hund's rule. And Hund's rule states that the stable arrangement of electrons in a subshell is one that maximizes parallel spin. So if you remember, this is what is known as paired spin. This is known as parallel spin because they're all heading in the same direction. And that is what we would want to do. So there is an order at which we put electrons into an orbital that is a subshell. And the order is we actually go one at a time. And then we go back and start pairing them off. So that will preserve sort of our maximal parallel spin all the way through. So whenever you have a subshell like a P subshell, a D subshell, or an F subshell, you always go in one at a time until you fill them all up, and then you go back and start pairing them up. So not 2 at a time into each orbital. So again, that happens over here at, what was it there? Carbon, I think. And carbon is 6. So as we talked about again, 2, 4, and now we could go into there. And if we write our electron configuration here for it, 1s2, 2s2, 2p2 in this case. Again, if you count up all the top numbers, 2, 4, and 6 electrons have been distributed into our orbital. Again, we would have the same sort of orbital diagram. We're going to go down, up, up here. And again, kind of going px, py, and pz here. So again, one at a time. So we obviously have now put 2 into that subshell. We still have room for 4 more. So let's finish out the first 10 here. And we're going to go to nitrogen next. Nitrogen is 7. So once again, starting up here, 2, 4, and we still are here. And that's going to get us to 7 in this case because we have enough to put in there. And if we write our electron configuration, 1s2, 2s2, 2p3, we have 5 on the second energy level and 2 electrons on the first energy level, as both of these are n is equal to 2, and this is n is equal to 1. In this case, if we were doing our orbital diagram here, again, we would go up and down, up and down, up, up, and up. At this point, we have maximized our parallel spin within that subshell. Any more electrons will have to go in the opposite direction, and we will start filling. Again, you go back to the left and work your way across. So let's continue on there. Number 8, which is oxygen, should be our next one. And again, 8 for oxygen, starting here, 2, 4, and we have enough to put it into there. And that will give us 1s2, 2s2, 2p4 in this case. And again, if you count up the top numbers, that should give us our total number of electrons of 8. Going in up, down, again, px, py, and pz, up, up, and now we come back and pair off that first one. So we put it in again all the way across and then come back the other way, left to right, and pair up those electrons. You can hopefully see we have room in this subshell for 2 more electrons, 1 in each of those, until this subshell is filled, and we would have to go to the next one. So we'll do number 9, which is fluorine, and that will continue to fill up this 2p subshell at this point, since we do have room for it. And let's take a look here. So again, we have 1s2, 2s2, 2p5 at the second energy level, and 2 on the first, which gives the ground 9 electrons. Filling in our orbital diagram again, we're going to go up and down, up and down, up, 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 and now come back down, down. And again, you can hopefully see here we have 1 more spot there before completely filled in this subshell. That, of course, happens with 1 more element down the road there, number 10 on the periodic table, which is neon. And because neon has 10 protons and it's neutral, it would also have 10 electrons, and that's good because we do have, again, our room right there for that last electron. So let's do neons, which is 10. Again, 2 into there, 4 into there, and again, we have 6 more we could put in there, which would be 10. And if we write our electron configuration at this point, 1s2, 2s2, 2p6, and we'll go up, down, up, down, up, 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 down, down, and down in this case. And we are now completely filled at this point. The next place that we would need to go is, we would then need to go to the 3s if we have more electrons to fill, again following that sort of zigzag order along the way. At this point, we have 8 electrons on the second energy level, and we have 2 electrons on the first. By the way, that is maxing out our second energy level, right? Because n is equal to 2, and 2 squared is 4 times 2, which is 8, and that is maxing out that second energy level, just like we maxed out our first energy level here of n equals 1. 2 times 1 squared is 2 electrons. So we have now maxed out both of those energy levels in terms of electrons. And again, that is where we need to go next, which is from here to here to here. And now we would need to go into our 3s if we had more electrons to fill. Any questions on that there? So why don't you do argon, right? The electron configuration for argon. Okay, so let's take a look. So 18, once again, we're going to obviously start up here. So that's going to give us 2, 4, that's going to be 10, or it's be 12, and 6, 18. So we do have to zigzag that way. So we should end up with here 1s2, 2s2, 2p6, 3s2, and 3p6. Again, if you count up everybody up on top, you should have 18 listed there. We also have 8 electrons on the third energy level. We still have 8 on the second and 2 on the first energy level. If we went with our orbital diagram here, again, we would need several boxes or lines. And again, we would go 1, 2, 3, 4, 5, 6, 7, 8, 9, and 12, 13, 14, 15, 16, 17, and 18 coming in. Again, we're completely filled at this point. And after our 3p, we would then go to our 4s before our 3d. So remember, this is right around where that sort of change occurs in terms of the energy, and you make sure you want to do that. I think over here has it. Stuff, yeah. So make sure, again, this is sort of that area where people kind of always want to go the 3 before the 4s, so they would go next. All right. Now, the off-ball principle is the idea that protons are added to the nucleus one at a time, and so are electrons. They're added not to the nucleus, obviously, they're added to the different orbitals from lowest energy level to highest, one at a time to those atomic orbitals. Now, if we did the electron configuration for potassium, which is 19, we would have 1s2, 2s2, 2p6, 3s2, 3p6. Remember, again, at this point, we are now going to go to the 4 first. So 4s1. Again, as you come through that, you will see your 3p to your 4s to your 3d. So again, that is the way we go here. Now, if we look at this electron configuration through this point of it here, through here is 18 electrons, if you count up the top numbers, 2, 4, 10, 12, 18 electrons. We just did 18 electrons, and that was, which one? That was argon. So you can kind of write a shorthand by putting argon in brackets and just continuing on with the electron configuration for S1 in this case. The argon here represents obviously what's in the green box, and you continue on with the configuration. Now, argon is a noble gas, and that is what has to go into this box. That does has to be a noble gas. That's group 8 on the periodic table. And it has to be the noble gas that comes right before it. So if you look on the periodic table, the noble gas comes right before potassium is argon. If we were doing something like magnesium, which is 12 electrons, 1s2, 2s2, 2p6, 3s2. If we take a look at magnesium's configuration through here, if you just count up the top numbers, that is 2, 4, and 6 is 10. That is 10 electrons. And if you look on the periodic table, number 10 is neon. So you guys put neon in parentheses and continue on with the configuration here. So it has to be always a noble gas that goes in the bracket. It has to be obviously the noble gas that comes before the element on the periodic table. And you just continue on with it. So sort of a shorthand, sometimes referred to as noble gas configuration, but again, that has to be a noble gas. And you can do it for anybody. Most people probably wouldn't do it until you get into maybe sodium and beyond, but you could technically do it. Obviously, before neon, you would have to go helium, and for anybody that's beyond the helium as well. But most people just write those out and stuff like that. So sometimes you'll see that sort of shorthand used. Any questions on that there? Now, transition metals have incompletely filled D subshells or give rise to incompletely D cations in there. Now, if you follow our normal sort of electron configuration sort of chart, you will get all the correct electron configurations. But when we get into transition metal, which is in the middle of the periodic table there, right between group number 2 and group number 3, we have our transition metals. There are actually a number of exceptions to the electron configuration that has been found experimentally to be more stable. And some of those exceptions are the two that you should be responsible for is chromium, which is number 24, and copper, which is 29. And they both basically have the same sort of exception. If you wrote the electron configuration using our chart, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d4 is what you would end up with. Or if you want to shorten it down, that would be argon, 4s2, 3d4. Same thing if you did it for copper, it'd be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d9, or if you wanted to shorten it down, it would be argon 4s2 3d4. So these are two exceptions, and the exceptions are actually right here in the last part of it. And the exception is it's been found experimentally that in chromium and also in copper, it actually has one less electron in the s orbital and one more electron in the d orbital. And the correct configuration should actually be at the end here, 4s1 3d5. 4s1 3d5. And the same sort of thing over here. This should be 4s1 3d10. And again, 4s1 3d10 would be the proper way. So they're able to do that because the s orbitals and the d orbitals are super close in energy, so it doesn't take that much energy for them to bump up there. It also, for example, for chromium maximizes parallel spin, and it does for copper, kind of fills up the d orbitals there. Now, if you look at chromium and copper on the periodic table and you go down and kind of in on both of them, now all those elements there's a ton of exceptions, like silver's an exception, PD's an exception. There's a bunch of these sort of exceptions that occur in the transition metal region. For example, PD has no electrons in the S's. They've all gone to the D's. So there is a lot, to be truthfully honest with you, in this area. But for our class, you will only need to remember chromium and copper. The other ones you could write the other way, but realize there are actually exceptions that are there as well. Should fill that there. All right, we will lay it up.